Okay, so good afternoon, everybody. I hope you can hear me. So if there is any technical problem, please, Simona, tell me so we can try and solve it. Okay, so I will put my presentation in full screen. My name is Riccardo Battisti and I work for Ambiente Italia, of course. And the topic of the webinar for today is solar energy for buildings. So the use of solar energy for covering the energy needs of buildings, both regarding heat and electricity. Okay, so as Simona was writing in the chat, you can directly ask questions during the presentation because of course we had to compress such a wide topic like solar energy in just 1 hour and a half, 2 hours. And so I will discuss about very different topics on solar energy, and so it may happen that you have questions during the presentation, so please ask them through the chat box, but of course you can also ask them at the end. Okay, so as I was saying in my introduction, we are talking about the use of solar energy for both heat production through the so-called solar thermal plants, solar thermal collectors, and photovoltaic, which means the use of solar energy for producing electricity, electric energy. Talking about solar energy, of course, the first issue is how to catch it. We all know how to catch it, but maybe we don't know, or we are not sure how to catch it in an optimal way. Let's put it like that. So, of course, the first thing is how to install these solar collectors. And now I'm talking about both solar thermal and photovoltaics, because there are some topics which are, let's say, common to both technologies. First of all, of course, the best thing is to install these collectors in order to follow the path of the sun during the day, which means that the orientation, the optimal orientation of these collectors should be towards south, so with the azimuth angle of 0, let's put it like that. So you see here in the picture, for instance, this collector has a very slight difference between the south orientation, which is again the optimal. Regarding the tilt, which is the, let's say, the tilt with respect to the horizontal line, this is a bit more complicated because, of course, it depends on the latitude. So the more you are going towards the equatorial zone, let's say, and the more the collector should be flat, so the tilt angle should be low. But of course, it also depends on the use you have to do of the solar energy you produce. So for instance, if you want to maximize the winter yield of a solar collector, then you have to increase the tilt, because of course during the winter season the average age of the sun above the horizon is lower than in the summer. While if you have to maximize, on the other hand, the summer use, then the collector should be installed with a tilt angle as low as possible. Of course, in most of the cases, the best solution is in between these two extreme solutions, because if you want, for instance, to optimize the average annual yield of a solar thermal or a photovoltaic plant at a latitude of, let's say, about 40 degrees, which is more or less central North Italy, for instance, then the tilt angle, the optimal tilt angle is about 30 degrees. Then I will show you a tool which is available online, which can tell you very easily and very quickly which is the optimal tilt for each location all over Europe. Again, as I said, there is an optimal solution for the positioning of solar panels, either thermal or photovoltaic, and you see it clearly from this drawing. So you have 100% of the energy that can be collected if, for instance, the collectors are put on the roof and they have a tilt of about, let's say, 30 degrees, and they are oriented towards south. But you can see also that if, for instance, I have to use other areas on the roof or even parts of the facade of the buildings, then you see that the loss in terms of energy collected from the sun, it's not that high. For instance, if you see this portion of roofs which are on the left and on the right, which means that are again about 30 degrees tilt, but they are not exactly towards south, then the energy loss is just 5%. So you can still collect 95% of the energy on these roofs, which means that you can still have a nice looking installation, which means, for instance, parallel to the roof direction, without having a large loss in terms of energy. So this is very good news, let's say, for solar energy. Of course, if you must use, for instance, the facade of the buildings, then you have a higher energy loss. For instance, here on the south facade, you have 70%. While on this facade here you have 65%, and even if you go east, for instance, you have 50%. But of course, these are not the optimal surface areas that should be used in buildings. But of course, the more you go north in Europe, and less important is this difference between installation on tilted surfaces on the roof and on facade. So in some Northern Europe countries, it can be very good also to install photovoltaic panels on the facades. Then, of course, the amount of solar energy that we can collect through these solar collectors is also influenced not only by the position of these panels, but also by the potential shadowing by some elements. In this case, you see in the drawing, of course, the shadowing by a tree, but it can be other buildings, especially if we are in urban environments. So, of course, what is important to estimate the shadowing is the distance from the roof where we are installing the solar plant to the obstacle, the height of the obstacle, and also its position with respect to the south. So all these elements should be considered. Estimating the effect of shadowing on the reduction of the energy collected is not an easy issue. It is usually done through specific design software, so it's quite a complicated issue, let's put it like that. But in many of the cases, fortunately, solar collectors should be put, of course, out of the shadow. So usually it's not, a careful assessment of the shadow is not needed. But just in case there are some potential shadowing elements, I really suggest the use of complicated tools, let's say, to estimate this shadowing. And then we have to say a very important thing, which is the first difference between this technology we are analyzing today, so photovoltaic and solar thermal, that photovoltaic PV is more sensitive than ST solar thermal to shadowing. So let's put it like that, that the energy loss due to shadowing in solar thermal is more or less proportional to the amount of shadowing, while for photovoltaic plants, let's say there are some technical problems which can even put one of the photovoltaic models out of the energy production if there is a good amount of shadow. So this means that for photovoltaic plants, the assessment of the shadowing problem should be more careful than for solar thermal. And of course, if we are talking about shadowing, and we are talking about medium scale and large scale solar plants, this means that these plants are composed by several parallel rows of solar collector, as you see in this scheme on the left and on this real plant on the right. This real plant is, for instance, a large scale solar thermal plant in Denmark. And you see, of course, that there should be a distance, kind of a respect distance between these parallel rows to avoid mutual shadowing between rows. How much is this distance? We can take this graph, which is in Italian, but it's very easy to understand. So on the horizontal axis, you have this tilt angle. So for instance, we can take 30 degrees, as I was saying before, so as a tilt for optimizing the energy yield collected during the year. Then you have several curves here, which are the latitude. So we can again take, for instance, 40 degrees of latitude, or 42, for instance. I'm in Rome, so Rome is about 42 degrees of latitude. And so if you look at 30 degrees of tilt angle and 42 degrees of latitude, then on the on the vertical axis you read 2. 2 is the ratio between the distance between the different parallel rows of solar panels and their length. So this means that the distance between the rows should be at least 2 times the length of the solar collectors. Of course, it's very important to respect this length. On the other hand, the larger is the area you need and the higher the cost, for instance, of the land or of the roof and so on. So you have to find a balance, a trade-off between lowering the mutual shadowing between these parallel rows and at the same time not increasing too much the area. So we can say as a rule of thumb that the area needed is 2.5 times the active area of solar panels. So if, for instance, you have to install 1,000 square meter of solar thermal or photovoltaic collectors on the ground, for instance, then you need an area which is about 2,000, 2,500 times. Of course, in this case, the more you go to the north of Europe, and the worse is the situation, because the sun age on the horizon is lower than in southern countries, and this means that the mutual shadowing between these parallel rows is more severe, let's say. So again, just to summarize, I go back. So we realize that to optimize the capture of solar energy, we had to install the solar panels possibly towards south and with the tilt angle that depends on the use and on the latitude, but basically we can say, just as a rule of thumb, that between 30 and 40 degrees is okay. So we can afford to install the collectors also in other positions in the building. We also saw that shadowing could be an issue. Of course, I could say that it could be an issue, of course, especially in an urban environment where you have a lot of buildings. And we also learned that for the photovoltaic technology, it's more important to have a careful assessment of the shadowing with respect to solar thermal. And we also learned that when you have a large plant, which is composed of different parallel rows of collectors, then you have to beware also of a mutual shadowing. And we also learned through this graph that can be applied for both solar thermal and photovoltaics, that this distance between the rows, it's about 1.5, 2 times the length of the panels. And this means that if you have to estimate the area which you need, it's about 2.5 times the active area of solar panels that you have to install. Now I would like to move to another topic which may look less, let's say, less technical, but at the same time it's one of the most important issues. In Italy it's for sure, but I'm sure that in many other countries as well. So let's say the visual and the environmental impact. I put it among brackets in this case because it's not always clear what is the impact, and in many cases I'm convinced that there is no real impact for solar thermal and photovoltaic, but there is a lot of discussion going on also at political level about that. So first of all, it's true that, of course, solar energy is less dense than fossil fuels, that energy coming from fossil fuels. So you need a larger area, a larger surface to produce the same amount of energy. But at the same time, we are talking about solar energy in buildings. So we are talking about solar plants which are installed on surfaces which are already occupied by the building. And this is my first message about this topic, so that areas are always available. So it's not true that in order to have a good production of heat and electricity by solar energy, we have to exploit all of our, for instance, agricultural lands, but we should look to other surfaces. So if you look at these 3 examples I put, these are solar thermal plants, so it's not photovoltaic. it may look strange, but it's an example from, actually two examples from Germany. So you see on the left, this is a carport, a car parking, and so the canopies protecting the cars are made by solar thermal collectors. So in this case, we are not using the ground for installing the collectors. We are not creating, I would say, neither a visual, not a land impact, a land use. In this case, it's even, I think, more interesting. It's still a German example again, and this is kind of a noise barrier put between the main roads and the area and the district where residential buildings are. So in this case, again, a surface was used, which is not agricultural, of course, and the solar collectors were placed here. And in this case, again, this is the most common case, we could say. So this is the gym of the district. By the way, of this district, you also have a carport. And in this case, so the solar thermal collectors were placed on the roof of the gym. So the message is there are plenty of surfaces available, and there is no need usually for putting also the collectors on the ground. You see here also two other examples. This is a very large, I would say very long noise barrier on the highway in the north of Italy. So this is also a very nice application because the noise barriers offer a very wide surface where to put solar collectors on. In this case, this is photovoltaic. And again, photovoltaic, this is a nice looking also application, and this is in the central train station in Berlin. So maybe you already know this application, and it's very interesting because they again use the roof of the station. Of course, there are also possibilities of going towards a nicer looking visual integration of the collectors. So you see here two examples, but of course there are plenty of these examples. On the left side, you see a pilot tile, let's put it like that, done with a specific photovoltaic tile, done in the north of Italy in a specific region where they have these peculiar tiles. And this was developed by Ambiente Italia, by the way. This was done in order, of course, to respect the shape of the typical roofs in this area of North Italy. And you see on the right here a different application. In this case is solar thermal, it's not photovoltaic. And you see this is a facade application in a student's house in Austria, in Graz, if I don't get wrong. And this is very interesting because you see that the solar collectors are perfectly integrated also from a visual point of view in the facade of the building. So again, the message is visual integration is possible. Usually, of course, it is a bit more expensive than, let's put it like that, than normal, that's standard commercial solar plants, but of course it's possible. And then you can go also to even more interesting solutions. So this is, for instance, an application in the Netherlands. And you see that in this case, this is a photovoltaic plant. And you see that spacing, leaving a space among the photovoltaic cells composing each one of the photovoltaic model, you see that some light can pass. And so this is a kind of a semi-transparent photovoltaic plant. And you see here on the right even a more innovative application of photovoltaic, where you see that the texture of the panel is more or less mimicking, reproducing the environment. So it can really be kind of hidden. Of course, such a model could be very expensive, and of course also its efficiency, its yield cannot be the same as the standard photovoltaic plants. So as anything that should collect solar energy, the darker it is, the better it is. So if you put something which is green, of course you would not expect a very high efficiency from that. But the message is if for special applications and for special requirements, let's say, we have to develop something similar to these solutions. So from a technological point of view, this is absolutely possible. And you see here also other interesting applications of solar thermal collectors, which are colored in this case, so with different colors. And again, they were put on the facade of these buildings, even with different colors. Again, you would not expect let's say, the best performance from these collectors. But again, the message is if we have to do something interesting, we can do it with both solar thermal and photovoltaic. Another issue, which is again related to the visual and environmental impact of this plant, is the use of the land. So, of course, it's not the best idea, let's say, to use agricultural land. It's not the first priority to install solar thermal and photovoltaic plants, but of course this depends also on the availability of the land. For instance, in Denmark, they use large solar thermal plants for feeding the heat into their district heating grids. But of course, Denmark is a low density country, basically, so that they can afford to have a low cost land and they can put these large plants. But I wanted to show here just that it's a double use, let's call it like that. Double use of the land is possible. So you see here it's a real situation on the right. So you see these sheep resting below the solar collectors. This is exactly one of these large solar district heating plants in Denmark. While on the left you see a rendering, so it's not a real plant, but you see that you have here alternate, let's say, rows of solar collectors and also of greenhouses. So you see that putting solar collectors, either solar thermal or photovoltaic, on some land doesn't mean that this land is lost for agricultural use. So again, this double use is absolutely possible. And then again, about visual and environmental impact, I just wanted to close this topic with a bit provocative slide. So just to show, this is a nice looking photovoltaic plant on a mountain hut in the north of Italy. And this is a huge cow, which makes really no sense in this case, puts in the same very nice looking environment as you can see here, and it's really quite close to the photovoltaic plant. Unfortunately, I couldn't put it in the same picture, but it's very interesting to show. So, and maybe to ask ourselves who looks uglier. And also if we look at the roofs in Rome, in my city, so you can see plenty of antennas in this case, and this is a very, of course, historical building. And so the question is, would really this roof look uglier in case you put solar collectors on that? So sometimes again, when we talk about visual impact of solar collectors, maybe we should really think what is true and what is not. So, and we also saw that there are really many solutions for, let's say, mitigating, for lowering this this impact. So we talk about so far about two, let's say, topics which were really common for both photovoltaic and solar thermal. So how to collect solar energy and how to maximize the collection of solar energy, and how also to install these solar plants in a proper way, also from a visual point of view. And we also look at the different architectural solutions that we saw. So again, if you have any question, please maybe also through Simona, just interrupt me and I will answer the question at any moment. So I would go on now, starting to talk about the two different technologies. So let's talk about some technical issues regarding photovoltaic first. So solar panels for the production of electricity. First of all, as I was saying in my first slides, I want to show you this tool. This tool is free, is available online. It's called PV-GIS, so photovoltaic GIS. And you see also here, of course, the web address, so you can then use this tool by yourself. And what are the features of this tool? First of all, as you see here, you can see for any location in Europe the radiation, the solar radiation, on a monthly basis or on a daily basis. But it's also very interesting because beyond the solar radiation data, this tool is also able to provide an estimation of the production of a photovoltaic plant in that location. So in this case, as you see here, it's performance of grid-connected photovoltaic. So we mean a photovoltaic system which is also connected to the electrical grid, as is the case in the majority of times in our countries. So in this case, you have to choose the PV technology that you want to use, the installed power of the plant. In this case, for instance, I put 1 kilowatt. The estimated system losses, in this case, I just left the value which was proposed by the system, which is a good, let's say, average value. Then you should put the slope, so the tilt angle. We were talking about that at the beginning, and the azimuth. And you also, and the azimuth, sorry, means that 0 azimuth means that the panels are oriented towards south. And you can also ask the tool to do an automatic optimization of the slope and of the azimuth. So you can ask the tool to, let's say, look for the best position of the solar plant, so in order to collect the maximum of energy. Then there is, let's say, also a different case, which is the tracking. Tracking means that the PV system is able also to rotate, to move in order to follow the path of the sun. Usually this is, of course, only possible in case of ground-mounted photovoltaic plants. So if we are focusing if our focus is on photovoltaic plants in buildings, on buildings, as is the webinar today. So in this case, we are not talking about tracking. So we are talking about fixed photovoltaic plants. Okay, so again, you can choose the main parameters of the plant in this fields here. Then you can choose a location. In this case, I put Milano, so in the north of Italy, just not to be too optimistic, because of course then the solar radiation data, for instance, in Rome are much higher. So I put Milano. So in this case, you see again, we have we have the possibility of looking at the location through a typical Google Maps application. And then you have the results. How are the results, let's say, reported by the tool? So you have on this column on the left, of course, the months of the year. Then you have the average daily electricity production. So this is kilowatt hour for the average day in January, or February, March, and so on. Of course, you see this value is increasing when we are going towards the summer. So you have the maximum in July. And of course, the minimum is in December and January. Then you can sum all these contributions, and you will have in this column here, so EM, the average monthly electricity production from the system. Again, it's kilowatt hour produced. Then you can have here in the last two columns the average global irradiation. So we are talking about, in this case, solar energy. So let's say that the first two columns are really electricity production, so electric energy, which is the most interesting topic for us. So it's really electricity we can then use in the building. And in the second two columns, you have also the solar radiation. Then you have yearly averages, but of course, for me, the most important parameter is in the last line. So in this case, we have almost 1,700 kilowatt hour per square meter, and you have a production of energy which is 1,270 kilowatt hours. So in this case, from 1 kilowatt of photovoltaic, so we put a photovoltaic plant of 1 kilowatt as a power, and we have as an output 1,300 more or less kilowatt hours per year. So this is really the most important parameter which gives us the energy yield. And this estimation is quite good as a first estimation if you want to see how much electricity your photovoltaic plants in your site, in your location can produce. So I really invite you to use this tool because it's very easy. You need about 10 seconds to generate this table, and you can also have it in forms of graph, and it's very again, it's very user-friendly. So, as we saw from the example I have just showed, what are the main, let's say, figures regarding photovoltaic plants and regarding especially its energy output, which is the most important parameter. So we just saw that 1 kilowatt peak photovoltaic, we always put this small p, so it's a kind of a reference unit. So 1 kilowatt of photovoltaic produces from, let's say, from 900 to 1,300 kilowatt hours per year. We can call this equivalent hours. So it's like we have an electricity production plant which can work this number of hours per year, because of course then the night comes, so the sun is not shining 24 hours, unfortunately, or fortunately, and so we have of course a limited production from the plant. And of course this range you see here between 900 and 1,300, it really depends on the location. So it's true that of course the sunniest the location is, and the highest is the energy production. What does it mean, this, from a user point of view? So, of course, you should look at your bill, but if we talk, for instance, just to talk about maybe an application, a user we know, if we talk about single residential user, which could have a consumption of about 3,000, 4,000 kilowatt hours per year of electricity, then to cover all of its electricity needs through photovoltaic, this user would need a 3-4 kilowatt photovoltaic system. So these are the main figures regarding photovoltaics. Of course, then each case is different, but we can say that these figures are quite close to reality usually. Another important point is to understand how much of the solar energy collected by the photovoltaic is then converted into electricity, so into useful energy for the user. So what is the conversion efficiency of photovoltaic? Of course, it depends on the technology we use, on the quality of the photovoltaic model we are purchasing. But let's say that we can have this range between 10% and 20%. We can look at this figure and we can say, okay, this efficiency is very low, but actually it's not a very important parameter at the moment, because of course solar energy is for free basically. So the only issue which is really affected by this efficiency is the area we need for installing a specific power of photovoltaic. So, as I was saying before, solar energy is has quite a low density if compared with fossil fuels, and this is quite natural because, of course, the solar energy is distributed all over the Earth, and this means that the quantity of solar energy we can collect per square meter on a specific surface must be low. And of course, the lower is the efficiency, the conversion efficiency of the photovoltaic, and the higher is the area we need to install a certain amount of power. So we can say that the active area needed, when I talk about active area, I mean the area actually occupied by photovoltaic modules. We need about between, let's say, 5 and 10 square meter per each kilowatt we want to install. So again, if we go back to the to this typical example of a single residential user, if you have to install a 3-4 kilowatt photovoltaic system in order to meet your energy needs in your house, then you would need a system which has an area which covers an area between, let's say, 15 and 30 square meters, something like that. And this is quite easy to look at because you just can look at the roofs of, especially where you have single houses, single family houses, and then you will see that more or less they have these surfaces on the roof. And I always ask this question, so is solar really a low density energy? Because sometimes, again, this is a fake problem, let's say. So it's true that, of course, as I already told you 2 times, that solar is a lower density energy with respect to the fossil fuels, but sometimes this is not really a problem for specific applications. So usually you have on residential roofs enough space to put enough photovoltaic for meeting the energy needs of that application. Of course, this can be an issue in very high-rise buildings, in high-density urban areas, but it is usually not an issue for smaller residential buildings, or, for instance, for schools, where you usually have a good roof area and the area that can be covered with the solar panels is usually enough to meet the electricity need of the school. So again, I encourage you not to say, okay, we don't have enough area, but really to do some easy calculations and maybe taking these figures as a reference, and you can see that usually your roof is enough. Another very important point, which is again, let's say, a characteristic of the solar energy in general, but now we are talking about photovoltaic. So can photovoltaic work alone? So that's why I wrote only you. Actually, sometimes we hear some people saying, okay, I would like to disconnect completely from the grid and, for instance, cover my wall needs with photovoltaic or with other renewable energies. Of course, there are some so-called standalone system. You see a scheme, a representation of the standalone system here. So you have in this case these solar panels, so photovoltaic panels. Then you have maybe wind turbine. So in this case you have a combination of 2 different renewable energies. But of course you also must have some batteries. So you must have some energy storages, because you are not connected to the electricity grid, and you cannot be sure that a photovoltaic or wind turbines can produce the electricity you need at the moment when you need it. So the, let's say, variable character feature of this renewable energy does not allow the user to completely rely on these sources. So this is a typical feature of renewables, And in this case, so in the standalone system, we have to install a battery pack. Of course, this increases the cost of the system, also the reliability and the need for maintenance. But let's say that the standalone systems are not very common in the European countries, and they are usually used for some remote applications, like for instance electrification of mountain huts and so on. So in the majority of the case, we are more familiar with this kind of systems where the photovoltaic gives free and clean electricity, but at the same time the user stays connected to the national electricity grid. So in this case, the operation of such a system is very easy. So you just have to give priority, let's say, to the PV panels. So in case there is an electricity need by the user when the photovoltaic plant is producing electricity because there is sun, it's sunny, then in this case the PV electricity is consumed within the building. So it's consumed directly by the user. If we have a surplus production, then this production can be injected to the grid, and we will see then how this is, let's say, remunerated. It depends really on the legislation and on the incentive system. But from an energy point of view, from a technical point of view, the surplus production which is not consumed within the building can go to the grid. And of course, at the same time, if our energy need is higher than the production coming by the photovoltaic plants, we can take from the grid the difference of electricity we need. So again, this is a very reliable scheme which is needed because we never know when photovoltaic electricity will be available. So we know, for instance, how much energy as an average we will have in January, February and so on, but we are not sure whether on January the 8th at noon there will be sun or not. So we really cannot rely 100% of the photovoltaic plant, but we are of course interested just in the energy savings that can be brought by these photovoltaic plants. Then there is a third scheme which is becoming more and more common, let's say more and more famous, especially thanks to the work which is being done, for instance, in Germany. So in this case, we have a photovoltaic plant which is connected to the electric grid, but at the same time, it also have an energy storage. So it also have a battery pack. And why do we need the battery pack if we are still connected to the electricity grid? Because actually the batteries, the energy storage can improve our self-consumption, let's say. So we can improve the amounts of the electricity produced by photovoltaic, which is then consumed in the building rather than sent to the grid. So in this case, if we have a surplus of energy production from the photovoltaic system, we should not, or we are not obliged, let's say, to transfer it to the electric utility, but we can store it in the storage and maybe use it in the night. So this is a very important point. Of course, this increases the cost of the system, but the cost of the energy storage of the batteries are getting lower and lower, and they are also financed in some, supported with an incentive in some of the countries, for instance, Germany again. And this is very important because increasing the self-consumption of the photovoltaic electricity is a key point to increase the economic viability of this system. We'll see it in a moment. So, trying to summarize all these figures, talking about costs and savings that can be given by the photovoltaic. Of course, these figures are very, I would say, country-specific, but I will give you an example for Italy, and I will give you then some tips, let's say, on how to estimate for your country. So let's take a 3 kilowatt photovoltaic system, again, thinking about a single residential unit. The cost could be 2,000 euros per kilowatt. Some years ago, it was about 5 times more, so 10,000 euros per kilowatt. So there has been a very strong decrease in the price, which is a very nice news. So at the moment, such a system could cost 6,000 euros, which means turnkey system, so installed. In Italy, I saw even lower prices, but I just wanted to put this price not to be too optimistic, let's say, so to be conservative. Then there could be some form of incentive for purchasing the system. For instance, in Italy, now we have this system for several years of tax reduction. So we can deduct from our taxes 50% of the investment cost. So 3,000 euros can be deducted from the taxes. So this is the cost. Let's look at the output. So what is the economic benefit of installing this photovoltaic system? We have an output that can be 1,200 kilowatt hours per year produced by 1 kilowatt, if you remember the example I did for Milano, for instance. So 1,200 times 3, because we have a 3 kilowatt photovoltaic system. So we have a production of 3,600 kilowatt hour per year, which means that as an average, it could cover more or less my energy bill, because let's say that a single user could have, again, a consumption which is between 3,000 and 4,000 kilowatt hour per year. Then it's very important to estimate the economic benefit of such a plant to be able to say how much of this energy produced by photovoltaic can be consumed at the same moment within the buildings. In this case, I did an estimation of 40% because this is the typical self-consumption rate that can be reached in a residential application. So given the fact that the people during the day is at work, so they are not consuming so much energy, and then there is a peak maybe in the evening and so on, and then you can estimate that 40% of this PV electricity can be self-consumed, so about 1,400 kilowatt hour per year, while the 60% of this energy is excess energy that should be sold, let's say, to the grid. So it's more than 2,100 kilowatt hours per year. So what are the savings? This, of course, depends on the economic conditions in the country. But let's put it like that. If I'm self-consuming PV electricity, for sure I'm not buying electricity from the grid. So the savings can be 1,440 kilowatt hour per year, which are self-consumed PV electricity, multiplied by the cost of the kilowatt hour I usually buy from the grid. So these are savings. And this is about 260 euros per year. Then this really depends on the legislation you have in your country. So for instance, in Italy, we have a kind of a premium. So it's not exactly an incentive like in the feed-in, so-called feed-in tariff period. So at the moment, we don't have any feed-in tariff, but we have kind of an excess premium. So for each kilowatt hour we give to the grid, we are rewarded, let's put it like that, with 9 euro cents per kilowatt hour. So you see that it's about half of the saving I can have with the self-consumption. So that is the reason why I was telling you that it's very important to increase as much as possible the self-consumption. And this can be done, of course, through behavioral change. So if I think about the schools, maybe it's possible to increase the self-consumption of PV electricity, but of course it can be done also about some home automation systems. So systems which are moving some loads from the evening to the day, for instance. So in this case, we see that, again, the savings bring this 260 euros and the excess premium brings about less than 200 euros. So if you look at the payback time, also considering this tax reduction, you have a payback time of the investment in about 6-7 years. So some conclusions about this cost and savings. some form of incentives is still needed. So this calculation is okay because we have a tax reduction of 50% in Italy. So we still have a good market of photovoltaic for residential application because we have this tax reduction. And especially because the feed-in tariffs are not available anymore in many of the countries. Then this excess premium will decrease for sure. So I think the let's say the direction set by the European Commission in the so-called winter package is very clear. So we have an excess of electricity in the grid, so we don't need more renewable energy producing excess electricity. So self-consumption should be encouraged, but excess electricity should not be. So this means that this excess premium will decrease for sure in all national legislation. Again, high self-consumption rate is very important to obtain. So this means, of course, that we maybe have to look at specific sectors for photovoltaic. For instance, commercial and industrial sector are very interesting because they concentrate their loads during the day. Schools, what about schools? Of course, maybe if we look at the daily consumption curve, it could be interesting because most of the consumption are during the day, but we also have to look at the seasonal variation. So for the school, of course, the summer closing can be a problem also because the summer is the best season for the electricity production by photovoltaic. So a careful estimation of these differences is needed to evaluate the economic viability of such system. And then, of course, again, if I look at the European legislation, but this is also happening, for instance, in Italy. So the electricity bill structures in the future will move some of the so-called system charges or grid charges, which are basically taxes. They will move it from the consumption-based part of the bill to the capacity-based, which means that we will pay more and more costs on the bill which are fixed, which are not related to how much energy we consume. And this means that even if we save energy, we cannot save those costs. So the economic profitability of self-consuming PV electricity could be lower in the future. So this is a very important discussion which is going on in many European countries. A solution which could be very good for photovoltaic plant is so-called power purchase agreements. What does it mean? It means that it's not the user who is the owner of the photovoltaic plant, but it's a third party. So it's an investor which comes, put the photovoltaic plants on the roof, and it is still the owner of the photovoltaic plants, but it can sell the electricity to the user at a fixed price. So in this case, the user is not assuming any risk for the photovoltaic plant, an investment risk, but it just has a fixed price. And of course, this works if the price which is offered by the investor is lower than the grid price which the user is paying at the moment. There are still some legislative barriers. For instance, in Italy, this power purchase agreement cannot be done with more than one user. So for instance, I cannot go as an investor and install a photovoltaic plant in a commercial center, in a shopping mall, and sell the electricity to all the shops in the shopping mall, because this would be a multi-user power purchase agreement, and this is not allowed in Italy, but also in many other European countries at the moment. Okay, so just to summarize what we say about photovoltaics. So we started with an estimation of the energy output from a photovoltaic plant, and you should always remember that there is this online tool available for free, this PVGs, which allows you to estimate the solar radiation in your location, but not only the solar radiation, also the energy produced by the photovoltaic plant. And I also tried to give some general figures on photovoltaic. So how much energy in 1 year can be produced by a certain amount of power, so 1 kilowatt of photovoltaic, for instance. What could be the need by a residential user? and what could be also the size of such a plant in terms of areas needed, for instance, on the roof. We also saw that photovoltaic cannot work alone, so either we need a battery or we need the connection to stay connected to the electricity grid. Even though there is also a possible combination of these two solutions, because it's quite typical now on the market to offer photovoltaic systems which are still connected to the grid but also equipped with an energy storage with some batteries. Then I tried to do an example calculation of costs and savings for photovoltaics, of course referring to a situation in Italy, but this is quite common also in other European countries. So referring to a 3 kilowatt system, which is the typical size for a residential plant, take into account, assuming, let's say, a tax reduction of 50%, calculating the output, and again, this is a very important point, let me say it once again, distinguishing between the energy which can be self-consumed, so at the moment it is produced, it is consumed within the building, and the excess energy which has to be given to the grid, because this has usually quite a different economic benefit. So the savings are directly related to the price you normally pay for the electricity you buy for the grid, while the excess energy you sold to the grid is usually awarded with an excess premium which is much lower than the savings. And again, this excess premium will most probably decrease in the legislation of the European countries if we look at the direction taken by the energy policy in the EU. So it's very important to achieve high self-consumption rate, also taking into account that the future electricity bill structures will shift some of these variable costs toward the fixed cost in the bill, thus limiting the benefits of self-consumption. And I also underlined the power purchase agreement, where a third party, an investor, came, installed the photovoltaic plant, and basically sells electricity to the user. Okay, we can move now to the solar thermal technology. Solar thermal is a much easier technology to understand. It's the production of hot water basically by solar energy, and we have here the typical collector which is used, I would say 85–90% in European countries, so the so-called flat plate collector. You see here the structure, which is very intuitive. So you have kind of a glass covering above the collector. Then you have some, for instance, copper tubes with a metal plate covering. Then you have this insulation, this yellow insulation on the back and on the sides of the collector. And so the goal of all this structure is to transform the radiation, the sun radiation, into heat, and so to heat some fluid which is flowing here in the tubes of the collectors. And of course, both the glass and the insulation material are there to, let's say, reduce the thermal losses, and so to guarantee that the hot water is produced and then transferred to the user. So you see here how is the operation of such a system. Sorry, here the color changed, so it should be blue, of course, in the lowest part. So the water enters the collectors and it's basically cold, and then it heats up in the collector and goes out on the top part of the collector and goes, of course, to the user. There are also some other technologies. So as I said, this is the most typical commercial application all over Europe. But then you have some other technologies. This we can call this a very poor technology, let's put it like that. So it's called unglazed collector because it doesn't have a glazing, so it doesn't have a glass coverage, and it doesn't have an insulation either. So you see just a large plastic tube in the sun, and of course this is very good when for application which are concentrated in the summer period. So you see an application here on the right, for instance, for a swimming pool. So in this case, this works very well. It's also sold, for instance, in some so-called solar showers. So it's for applications or for campings, for instance. So it's really for applications which are during the summer and not all year long. Then I would say, sorry, that the market share, let's say, of such technology in Europe is almost zero. So it's quite a typical application in the US, where you have this urban solutions where with single family houses with a lot of small swimming pools, but it's not really typical in Europe. While let's say that 10–15% of the market in Europe is done by systems which use evacuated tube collectors. So what is the idea here is the thermos principle. So if you want to reduce the thermal losses towards the outside environment, you can evacuate, so you can take the air out of the collector. And so you usually see these collectors, which are composed by a number of tubes, and inside each one of the tubes there is the vacuum. So this is a typical application also in the European market. Okay, I'm not doing any, in this case, any discussion about the solar radiation, because the same tool I showed you, the PVGs, so this online tool, which is available for free, I showed you for photovoltaic, but of course it can be used also for solar thermal. There is no tool for estimating the production, but you can use the tool there to look at the solar radiation values, and then you can assume a value for the conversion efficiency, and then you can understand how much heat, how much hot water can be produced by a solar thermal plant in your location. So in this case, if I look at again at 1 square meter of solar thermal, just to have a reference value, it can produce between 400 and 700 kilowatt hour per year of heat. What does it mean? Again, if I look at this value from the point of view of user, means that if we look at a residential user that uses solar thermal for the production of domestic hot water, we can say that we need about 1 square meter of solar thermal per person for covering about 3/4 of domestic hot water. So that is the reason why, if you look at the roofs of residential applications, when they have solar thermal, you see these typical plants composed usually of 2 collectors, which are 2 times 2 square meter. So basically, one residential application with 4 square meter, because this covers approximately the need of 4–5 persons in the house. Of course, if we want to cover not only the domestic hot water need, but also partially the space heating load, which is usually much higher than domestic hot water need, especially if the house is not very well insulated, then of course the size of the solar thermal plant becomes much larger. For instance, this picture you see on the right, it's is a solar thermal plant for an agritourism in the north of Italy, and this is covering both domestic hot water needs and space heating need. So in this case, solar thermal is operating together with a LPG boiler, where LPG is very expensive, and so the savings by solar thermal are very important for the economic balance, let's say, of the owner. Of course, this range I put up here, so the production of 400, 700 kilowatt hour per year. What does it depend on? Of course, on the how sunny is the location. So again, the amount of solar radiation which can be collected in the site, and also it's very important the temperature at which you need the hot water. So that the higher is the temperature, the lower is the efficiency of the plant. That is why a very good application of solar thermal is the production of domestic hot water, because in this case temperatures needed are quite limited. And also if you have to combine, to use, let's say, solar thermal for space heating needs, then it would be better if it's possible to combine solar thermal with some low temperature heating, right? Like for instance, radiant floors or something like that. What is the conversion efficiency? So how much of the solar radiation coming from the sun can be converted into heat, into hot water basically? In this case, the conversion efficiency is between 30 and 50%, depending on many parameters, for instance, the climate, and for instance, also again, the temperature of heat production. So you see that this conversion efficiency is much higher than for photovoltaic. And again, I'm asking the same question. So is solar really a low density energy? So of course it's less dense than fossil fuels, but again, if you look at residential applications, you see that usually 1 square meter per person is enough to cover the heat needs, for instance, for domestic hot water. So usually the space, the area which should be available on the roof for such a system is very small. So again, even though solar is a low density energy, usually this is not a problem. This is not an issue, a practical issue for the plant realization. Let's have a look again at the same problem of, let's say, energy independence that we examined for the photovoltaic. So is it possible for the solar thermal to operate alone? Also in this case, I would say that it doesn't make sense at all, even more than in photovoltaic, because photovoltaic is anyway connected to the grid. In this case of solar thermal, there is not a heating grid unless you have a district heating grid in your location, but this is not very common. So photovoltaic is always operating usually in series, let's say, with a conventional boiler. So in this case, you see here, in this scheme, you see the conventional gas boiler, for instance. Then you see the solar plant, the solar panels here up on the left. And then you have, okay, the scheme is quite complicated, but you don't have to look at the whole scheme. You just have to look at the storage. So here you have a water storage, which is the water storage used for domestic hot water, for sending the domestic hot water to the user by this arrow here. So basically, you have this water storage where you have two heat exchangers. One of them comes from the solar part, and one of them comes from the natural gas boiler. So let's call it from the conventional part. The important thing is that the solar heat exchanger is operating in the lower part of the storage. And this is done because, of course, the storage has a stratification of temperatures. So it's colder at the bottom and warmer at the top. And we have said that the efficiency of solar thermal is depending on the operating temperature. So if you put the solar thermal as a preheater in this kind of hydraulic plant, then you can reach a much higher efficiency. So that is why we always put the solar thermal in the lower part and the conventional boiler gives, let's say, the additional heating if of course is necessary, because then if you look at the operation of this plant, usually during the summer season, but I would say even before, so when the heating season is over, then usually the storage is heated up 100% by solar thermal. So you really don't need to turn the boiler on. Okay, this is happening automatically. So let's say so that the boiler is not turning on because the temperature reached by the storage, thanks to the solar thermal, so thanks to the heat produced by the solar thermal, is enough to feed the user with domestic hot water. So you see here how this is in reality. So you see here on the right a picture, a photo of two heat exchangers, serpentine heat exchanger storage. And you see here also that usually these systems are sold as a kit which is really a turnkey kit, so it's really ready to use. So all of these components, which are quite complicated and which you see here in the scheme, are usually, you can see it in this picture here on the bottom right, you see that all of these components, for instance, the regulation part, the expansion vessel, the pump, and so on, all of these components are already on the storage, let's say. So what the installer should do is just to connect the solar in the lower part and the boiler on the upper part, and then the operation of this of such a system is completely automatic. There are two kinds of system. One of them is the one we have just saw. So you have a pump for making the water circulate inside the solar thermal plant, and it's called the pumped system or forced circulation. While you can also have thermosiphon systems. This is quite typical, for instance, in Greece, in the south of Italy, and in other hot, warm countries, let's say. So in this case, you don't need a pump, so you just using the natural effect of the fact, because of course the hot water is lighter than the cold water, and so it goes up, and then it exchanges heat with the storage again, which is above the collector, above the solar thermal collector in this case, and then the cycle is completely automatic. And you can see here an example. Actually, this is very strange because this is installed in the north of Italy, where you usually don't have such kind of examples. And also in Central and Northern Europe, I think these systems are not very common, especially because, of course, even though this storage is insulated, it is anyway outside of the building. So in very rigid and cold climates, it's not the best solution to have this heat storage outside of the building. Let's try to do a calculation similar to what I did for the photovoltaic system, also for the solar thermal system. So we have, for instance, a 4 square meter solar thermal system. The cost can be estimated as 1,000 euros per each square meter you have to install. So you can talk about 4,000 euro for a system which is again the typical system for instance, a single family house. So 1 square meter per person, you can assume a 4-person family, and then you have this cost of 4,000 euros again for the turnkey system. You see here such a system, maybe this is even larger, a bit larger. Again, I put a tax reduction here, which is a quite typical incentive scheme for solar thermal of 50%. So similar to what I did for photovoltaic. Actually, in Italy, for instance, at the moment we have 2 incentive schemes for solar thermal. One of each is actually, one of these is a tax reduction, but it's even higher, so it's 65%. But in this case, for this calculation, I assume the 50% tax reduction. So basically, you can recover 2,000 euros from your taxes. What is the output? So I assumed that each square meter can produce 500 kilowatt hour per year. So if I go back, I told you that the energy output can be between 400 and 700 kilowatt hour per year. So in this case, I chose a value which is 500. So again, the output is 4 times 500, so it's 2,000 kilowatt hour per year. What is the benefit of this heat production? Of course, it depends on the conventional energy source you're replacing with this solar heat. In this case, I assumed not a very good case for solar thermal because I replaced natural gas, which is the cheapest actually conventional fuel. So I assumed a price of 0.8 euros per cubic meter of gas, which can be typical for residential applications in Italy, which means that you have a saving of 200 euros per year, and therefore a payback time of 10 years. Of course, in case you are replacing, for instance, electricity because you are producing heat through electric boiler, or as in the case I showed you, you're replacing LPG, for instance, then since these fuels are more expensive, then you can expect higher savings and therefore lower payback times. Okay. So just to summarize what I talk about on solar thermal, I showed you which are the most common technologies, especially in the European market. I told you the flat plate collector, which is the typical solar panel, let's say, covers about 90% of the European market. We also have, let's say, cheapest collectors, which can be used for summer-only applications, which are not very used in Europe. And then 10% of the European market is also covered by evacuated tubes collectors, which are high-performance collectors due to the fact that you have no air inside the collectors, and so thermal losses are reduced. Then I try to give you some figures about the energy output of solar thermal. So from 1 square meter of solar panel, we can get between 400 and 700 kilowatt hour per year, which means that if you want to produce domestic hot water, you need more or less 1 square meter per person in residential use. Of course, if you also want to supply some heat for space heating, you need a larger surface. And the conversion efficiency of these solar collectors is between 30 and 50%. Then I showed you how this is in real plants. So starting from pumped system, where you have a pump for the circulation of the heat carrier, and you have this storage, this water storage with 2 heat exchangers, one coming from the solar thermal and one coming from the conventional boiler. We also saw that especially in warm countries we can use these thermosiphon systems, which are very simple because they don't need a pump. But of course in colder countries this could be a problem because you have this boiler which is insulated, but anyway it's outside of the building, so you can have higher thermal losses. Then I tried to do a calculation for this system. So I took a 4 square meter solar thermal system, which can be typical for one family, assuming a cost of 1,000 of, let's say, in total 4,000 euros, and assuming a tax reduction as incentive scheme of 50%. And then we look at the output, and we assumed that this solar hot water was replacing natural gas burning, and so the savings were estimated at 200 euros per year, and the payback time was about 10 years. Okay, so after talking about these 2 technologies and trying to give an overview of these technologies, especially about the main production figures, I just want to tell you briefly about some programs and initiatives where you can look at also to get more information, which is maybe more related also to your project. So in the UK, there was a Run on Sun program, if I don't get wrong, led by the Friends of Earth. And it's very interesting because they were installing photovoltaic plants, in this case on the roof of on the roofs of some schools. And it's very interesting also to have a look at their website and to download their report, because there are several, let's say, how could I say, practical comments and suggestions also by the teachers and by the students, of course, involved in the development and installation of this photovoltaic system. So in this case, you see here two interesting sentences. So no disruption to electricity supply. So there is really no problem in combining photovoltaic with the normal electricity supply, and also that the panels look great. This is very important for what I was saying before about the visual impact. So there is not really impact, or let's say it's a positive impact, and they even say that the panels are very modern. So there is an innovative, let's say, visual impact. And of course, since they are installed on school, it is very important also the educational role of these plants. So having a plant there can really work like a permanent, let's say, educational resource. So you can have a look also at this other program they have in the UK, so the solarschools.org.uk. You can have a look, and you can, as you see here, there is a map with all the locations, and so you can really check all of the project to see, for instance, what is the installed power, which were the costs, and so on. And they were they really used a lot of different schemes. So with power purchase agreement, using a third-party investor, then selling the electricity to the school, to even the crowdfunding done within the families of the students. So it's very interesting to see also how they use this several solutions to implement the plans. Then I also wanted to show you this project we did also in Ambiente Italia some years ago. So repowermap.org is also the web address of this interactive map on renewable energies. Now here is in Italy, in Italian, sorry, but I can tell you just briefly what it is about. So you have here a map of renewable energy plants. It's not a statistical, let's say, map. So it was filled in on a voluntary basis, but as you can see, there are really a lot of plants in this database already. And this includes really photovoltaic, solar thermal, but also wind energy, biomass plants, and so on. And it's very interesting because you can really find here the exact location of the plant, usually with some technical characteristic and also with a picture. So you can have a look at your site and you can have a look whether there are some plants in the neighborhood which you can visit and have a look at. So I think it's very interesting also as an educational resource, this repowermap.org, which is still going on. So this web map is still maintained and it keeps on adding renewable energy plants. Then as a last resource, I just wanted to point out these projects. This project we are just finishing, now it's closing at the end of June. It's called PV financing, and as you can guess, this is about financing photovoltaic. So as I told you, in many countries now we don't have any more feed-in tariffs for photovoltaic, which means that there are no large incentives for electricity produced by photovoltaic, and so the economic viability of photovoltaic is much less high, let's say, than in the past. And so we really need to understand which kind of financial models are available for photovoltaic. And so we develop a series of documents and tools which are of course available for free for different European countries, so Austria, France, Germany, Italy, Spain, Turkey, UK, and also some of these documents and tools have been developed at a European level. What you find on the website, you find some financial schemes for developing photovoltaic, so which are the benefits and the problems with this financial scheme. You see also some real good practice examples coming from all these countries. You see you find the implementation guidelines. In this case, these are not in English, but these are in the national language of the country. Again, in the national languages, you find some policy papers, and maybe even more interesting for you could be the contractual models. So for some of the business models, let's say, that we can use for developing photovoltaic, for instance, leasing or power purchase agreement or crowdfunding or whatever, there are some contractual models available on the website. And also these contractual models have been developed in the national language of the country. And then you have a profitability calculation tool. So of course it's a simplified tool, but it can work very well for a first assessment of the photovoltaic profitability. And in this case, you can have it in all the languages of the countries I showed before. So I came to the end of my presentation. I try again to condense a lot of information in just one hour and yeah, almost 2 hours, let's say. And I thank you for your attention. Of course, if you have any question, I leave you here all of my contacts, and you can ask them, of course, also through Simona and Roberto. And I don't know, of course, if you have any question, we still have some time now. Any? Okay, just wait 1 or 2 minutes just to check whether there are some questions. Okay, it's not a question. Thank you. But of course, again, if then during the, let's say, practical work you have to do, then some question may arise, and then just in case, again, you can contact me through Simona and Roberto. So thanks again for surviving, let's say, this almost 2-hour lesson on solar energy. And again, please write me for any question you may have on that. Thank you. Sorry, just maybe is the presentation going to be online, and where can we find it? So this is a question, maybe I ask it back to Simona. Maybe you can answer in the chat. Of course, I make it available. Okay. So maybe Simona could even send you the presentation by email for me. Of course, it's okay to make it public, let's say. Okay, if there are no further question, I say thanks again for being patient, and yeah, and all the lesson has been recorded, and so also the recording will be made available to you. So just in case, you can have a look again at the lesson, and you can have maybe some questions. Okay. Thank you again, and goodbye.